Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my pleasure to introduce Nate Foster, professor at Cornell, who's been working on programming languages and in the past few years applied programming language techniques and all the tools of the discriminating hacker, including Haskell, Coq, Python, and of course Z3 for formal foundations of networks.
Thank you. So I'm going to talk today about some work I've been doing on really trying to provide the same kind of rigorous formal foundations for networks as we have for ordinary software. It's really fun to be here because you guys have been doing this for at least a decade now with projects like Static Driver Verifier and SLAM and Boogie and Z3 and all these tools. So we're trying to do the same thing for networks. I should start by acknowledging this is joint work with a proof assistant, both the tool and the people who did the real work. So Arjun Guha, who I think may have interned here several years ago, he's a postdoc in my group right now. He's on his way to UMass to start a faculty position there. Mark Reitlbatt, PhD student in my group, and Rebecca Coombes, who's an undergrad working with me. So they, of course, did all the real work. So the goal of what we're trying to do is to really provide a rigorous formal foundation for doing precise reasoning about network behavior. And as motivation, you just have to kind of look at the headlines and see that networks are both becoming really important for the operation of big cloud systems and also really fragile. So just kind of picking through the last couple of years, GitHub had a major outage last year in November, took down their whole site for over a day. And afterwards, they did a postmortem, and they released this little snippet saying what had caused the problem. And it turns out that they had a misconfiguration in one of their routers, and this caused a bridge loop in their network and eventually caused sort of the loss of connectivity for their whole site. Amazon had a similar kind of outage in April of 2012. A very similar kind of thing. They were doing some planned maintenance, and they were changing the configurations of their EC2 network. And they had a sort of really complicated series of cascading failures. But basically, they did a misconfiguration, sent way too much traffic onto a backup network, and then sort of overwhelmed a bunch of storage systems and eventually took down their whole East Coast data center for quite a while. GoDaddy had a similar outage where their release was very vague. So some series of internal network events corrupted their router tables and took out their DNS service and the DNS of a lot of their customers. And my favorite one, United Airlines had a network connectivity issue internally a couple years ago, and this sort of took down their whole computer system and actually led to a full ground stop at San Francisco. So networks are both really critical infrastructure, both for kind of Web 2.0, cloud computing, data centers, but also for companies like airlines. And yet, we're still kind of building them using very rudimentary sort of 1960s, 1970s era software techniques. And this is becoming a problem. So if you're someone, I think, from the community that we all come from, sort of programming languages, formal methods, and so on, you might wonder why it's so hard. And I want to kind of take you through a picture of kind of what an interaction sort of over the internet looks like, and just how complex the network actually is. So we'll start out with sort of some hosts, and pretend that you want these hosts to connect to some servers somewhere in some data center on the other side of the network. So the hosts are maybe connected on some kind of local area network through a bunch of Ethernet switches. And on the other side, you have the servers that are actually providing the service you're trying to connect to. And they're connected by a bunch of IP routers. And then maybe they're sitting behind some kind of load balancer so that incoming requests from the internet can be spread amongst these servers. And then you have some kind of gateway router that's hooking up the internal network that the servers are on to the network that the hosts are on. Of course, there's other kinds of networks, other ISPs. So you also have devices running BGP. Because you have outside traffic coming in, you need things like firewalls. You might have wireless hosts, wireless access gateways, middle boxes to do things like recording traffic for lawful intercept, and so on. And so, what we tend to think of the internet as sort of a very simple pipe that sort of gets packets from here to there. But actually, there's just a whole host of different kinds of devices that are involved in providing that kind of functionality. And so each of them, is usually provided by a different vendor. It's configured using a different language. And yet, the behavior of the whole system is somehow sort of the composition of all these things. And so if you want to reason about even fairly simple properties, you actually have to reason about a bunch of different devices, a bunch of different languages, and a bunch of different programs all working together. And in practice, the sort of complexity of dealing with all this makes it effectively impossible. So there's a recent trend from the last few years, though, that sort of has the promise of simplifying all of this. And that's called software-defined networking. So this kind of started out of Stanford a few years ago. And the basic idea is to greatly simplify the architecture of networks and replace all of these complex devices and languages with very simple and standard kinds of devices. So it's an area that kind of started out in data centers, but has started to sort of ripple out into other kinds of networks as well, including enterprise networks and even carrier networks. So the two big ideas in software-defined networks that make it possible to kind of start to do the kind of rigorous software engineering practices and also formal reasoning are first, just to kind of rip out the very complicated, very idiosyncratic, different network devices and replace them with a standard kind of device that has just a generic set of features. So that's idea one. And idea two is to actually decouple the parts of network devices that implement things like routing protocols and take them off of the devices that actually provide connectivity and even put them together into a maybe centralized kind of machine that's going to control the whole network. So these are the two ideas, just generalizing devices and standardizing them, and then decoupling control from forwarding. So the benefits of doing this are, well, first, if you want to deploy new kinds of functions in a network, you now have a kind of standard computer that you can program. This hasn't been possible before. And second, if you want to reason about the behavior of a network, you now have a very precise specification of what the network devices should do and what kinds of programs they're going to run. And so unlike the picture I started out with, where you had this sort of huge conglomeration of different devices and reasoning becomes practically infeasible, here you have a very clear specification of what programs are. And so you can start to write down things like formal specifications and check that your network obeys those.
So that looks like a single point of failure in the grid models.
Yeah, so this is a cartoon version. No serious deployments can have a single controller. You're going to have a replicated group of controllers, and those might control sort of one administrative domain. And then, of course, they'll have to talk to controllers in other domains. So you're still going to have all the kind of fundamental complexity you have in the internet. But you can get some leverage by viewing a tightly replicated group of controllers as implementing sort of one program. So you're not stuck with sort of reasoning about distributed protocols all the time.
Are you going to explain control plane, data plane? I've heard these terms before. I always get confused.
Sure.
Okay.
So the sort of classic architecture for things like internet routers and switches goes back to the first ones that were built sort of in the 80s, places like UCLA. And they basically divided the functionality of these boxes into two separate components. So the data plane is usually a custom piece of hardware that actually implements the switching fabric for a router or switch. So it basically has a bunch of ports, and it just forwards traffic very efficiently across those ports. And it sort of has one data structure that determines its behavior, which is a hardware table that says sort of what to do with certain packets coming in, where they should go. Above that, you need some other kind of device that's going to do things like compute paths through the network. So it's going to run all your classic routing protocols. And that's typically a general purpose CPU that's sort of coupled to this data plane. And it runs these distributed protocols, talks to other routers, and then computes paths, and then reconfigures the data plane. So in traditional network devices, these things are sort of sold together as one integrated unit. And so if you want to express some kind of control algorithm, you have to figure out how to sort of factor it into a distributed algorithm that runs on every individual device. And you also have to figure out how to encode it using vendor-specific, Cisco iOS or Juniper, their specific configuration language. So the difference here is just this thing is like, an ordinary server running a C program, and it's separate, but the interface that it uses to configure the data plane is completely standard.
deployment of this software switch?
Yeah, so I hate to sort my talk is not actually about software-defined networks. This is just sort of the technology that enables the work we're doing. But it's very real. So Google uses it for their inter-data center traffic. They do sort of global traffic engineering and get great efficiencies by doing this. And the other sort of huge success story is VMware bought the big startup out of Stanford and Berkeley, Nicira, last year. And they do virtualization for data centers. And I don't know all their customers, but eBay uses them, Rackspace, there's a few others.
So you're saying that internally Google, they had to buy a totally new set of routers, essentially, to do that?
My understanding, actually, so don't quote me on this because this is not my area of expertise, but Google was starting to do a sort of homebrew solution to this. So they were building their own switches, and then sort of software networking sort of emerged, and vendors were providing switches that could be programmed in this way. And so they jettisoned the homebrew solution and switched to, I don't know the vendor, but there are a bunch of real vendors that provide switches that work this way. And they switched to those.
So these companies like Cisco and Juniper Networks that were providing the old kinds of boxes, are they now providing the boxes that fit this new architecture also, or is this a new breed of companies?
So the companies that I think are most excited about this are the companies that are not the dominant ones right now, because it's a very disruptive kind of thing, and it kind of gives them an opening to a market that is not open to them right now. But even Cisco, for example, has what they call it, an internal startup that's looking at this kind of architecture. The real catalyst for this, I think, is actually data centers. If you want to do something interesting with a data center network, using traditional network devices makes this very difficult. So you actually, if you have one administrative domain of control, you'd really like to sort of run one program. So that was kind of the huge blind spot that let this open up. OK, so just as a sort of motivating example of the kind of properties you'd like to check, I want to show you a really, this is like too simple, but it still exhibits a bunch of features that make it interesting. So here's a network. It just consists of one device connected to 4 machines. And we have a sort of simple high-level policy that we'd like to get this network to obey. So first, it has a security component. So we want the network to provide connectivity, but block all SSH traffic. Second, we have some kind of monitoring policy. So we'd like all web traffic to be sent to the logger, which is sitting there on the left on port 4. And maybe we're going to do some kind of analysis for intrusion detection or something. And then lastly, all of the traffic between the clients, we'd like to just that traffic be forwarded as long as it's not SSH. So how could you implement this kind of thing in one of these software-defined networks? So basically, you have switches and a controller. And the switches give you one kind of data structure that you can program. And that's a forwarding table. So a forwarding table consists of a linear sequence of rules organized by priority. And each rule has a pattern that matches a set of packets, a list of actions that say what should happen to packets that come into that device and that match the pattern, and then some counters that keep track of basic statistics about the traffic. So here's a sort of partial buggy implementation of the policy I just showed you. The highest priority rule says any SSH traffic should just be dropped. There's no actions for those packets. And then any traffic to host 1 should be forwarded out port 1. And then all other packets should be diverted to the controller, which might decide to do something special with them. So this is one piece of these switches, and they just have this forwarding table. And then the other piece is the controller, which basically receives events out of the network. So things like the topology of the network changing, switches entering and leaving, links coming up or down. Also packets that might be explicitly diverted to the controller. The controller receives and then can choose what to do with them. And it can also receive statistics about how much traffic has been traversing particular switches and links. And the way that it manages the network is basically just by manipulating the forwarding table. So it can send on messages saying, please install this rule, please delete this rule. And it can also do things like query the counters in the rules. Okay, so it's a very simple kind of interface for programming a network. Nick?
So the switches at the bottom are also raising events and talking to the controller that way? So in addition, you said the controller receives events like change in topology or a link is down and so on, right?
Yep.
So are those events being also programmed in the switches and sent up to the controller?
So a switch that implements one of these software-defined networking protocols, like OpenFlow is the most popular one, they basically run a little agent that sits on the switch, and they the first thing they try to do is sort of connect to the controller. So there's kind of a handshaking that happens. The switch says, hey, I'm here. The controller says, hey, I'm here. They exchange information about their features. And then at that point, the controller receives a switch-connected event, which it can then record, remember that that switch is there. It also receives an event to say how many links there are and whether they're up. And so it can use this to do things like compute a picture of the overall topology of the network. In addition, I had an example on the last slide. Switches can divert packets to the controller.
Right.
So they can. One of the actions you can do is send a controller. And this is useful if you want to do something that can't be expressed as a rule in one of these tables. Then you can use the controller to do some general purpose computation and then push down new rules that maybe implement that.
So is the asynchrony and the kind of currency that's going on all managed by the runtime? So in other words, the controller, like if it wants to push out changes to the routing tables, it just happens automatically, or is there some kind of thinking that has to go on in that?
There's a lot of things that goes on, and that's one of the things I'm going to talk about today.
Okay.
So basically, the specification document for OpenFlow says sort of what switches have to do when they receive control messages, but there's a lot of reordering they can do. So you actually have to be quite careful and use low-level synchronization primitives to sort of get the switch to do the right thing.
Get it right.
Yeah. OK, so now let me step you through sort of 3 sources of bugs that make it actually difficult to program even this kind of simple machine. So one issue is that we kind of think of the controller as sort of beaming down a configuration for all the switches in the network. So its job is sort of to take, maybe it computes some complete list of a forwarding table that it wants to be installed on some switch, and then it can basically send messages to the switch that do that. So here's a table that implements our security policy from the first slide. I won't take the time to pronounce it, but you can trust me that it sort of completely captures the security monitoring and forwarding policy. And so the first thing you do in one of the controllers, say for OpenFlow, is to write a handler that says when a switch connects. So here's a Python function that says when the switch joins. Then I'm going to send it a sequence of messages. These messages basically contain rules, right? They have priorities, they have patterns, and they have actions. And so these are going to get beamed down to the switch, which will then configure its state to have this table. But of course, one thing that can happen is that a network is a distributed system, and so there's kind of events happening all the time. And while these messages are coming down from the controller, there could be packets that are arriving at that switch. And the default behavior of one of these switches is if the packet comes all the way through its table and it doesn't have a rule that says what to do with those packets, then it's going to divert them to the controller and generate another kind of event. In this case,
that it would drop it.
The default, so there's kind of an implicit rule at the bottom that says anything that unmatches go to the controller.
Okay.
If you want to drop, you have to say anything that matches at the bottom, drop.
Okay.
So the point is that we have to actually define sort of 2 implementations of our overall policy. One, the explicit rules that get sent onto the switch, and another that sort of resides in this handler for diverted packets that sort of applies the same thing. And you might wonder, well, this is silly. Why do I ever want to divert packets to the controller? Well, one issue is that you might be trying to implement some function that actually can't be expressed on switches, and so you have to do some processing on the controller. Another reason is that there are things like the switches have finite space in their tables, and so even if you sort of can compute a complete table that implements your policy, you may not be able to fit it, and so you might have to do things like sort of like paging in memory and basically move rules on and off the switch as you see traffic. So you end up having to actually implement sort of the same policy multiple places in your control program. And of course, anytime you have sort of replicated functionality, it's easy to make mistakes. And I actually have a bug here in my packet encode. It doesn't correctly do the SSH filtering. This is in general sort of a problem that you sort of end up writing the same policy multiple places in controllers. An even more worrying problem has to do with some of the flexibility that switches have to reorder the control messages they receive. So I claim that this first handler I showed you for switches connecting would basically take the table that we wrote down and sort of beam it down to the switch. So as a programmer, we kind of think that what's going to happen is the switch starts out with an empty table. We send down these messages, and then we get to a table that implements the full policy. But what can actually happen is, oh, sorry, this is what we think is going to happen. What can actually happen is that the switch receives all of our messages, it buffers them, and then it decides to reorder them. And it does this because actually some of these patterns in hardware involve sort of configuring multiple tables. And so it might choose to do the cheap ones first that only involve one table, and the more complicated ones later. And this is bad, of course, because while the network's in this state, if it's processing packets, we're actually not implementing our policy correctly. So we're letting SSH traffic through.
But I thought the order was important. I thought this was like a chain of fitness.
So the solution is that you have to actually use explicit barriers to synchronize with the switch and say, please process all the messages I sent you so far. So,
but I thought the order in which you have these rules was actually, like the semantics of the blue thing, the order matters. So you intend it to be in that order.
it does. So this is a Python program that executes sequentially. So it sends these messages down to the switch. The switch has to receive them in order. But the switch, per the specification, is completely allowed to reorder them as much as it likes.
Okay.
There are good reasons for this. Some messages are cheaper to answer than others, and some messages are more urgent than others.
Okay,
so
I can think of like this thing as having a little optimizing compiler in it, and if I want to prevent it from optimizing, then I have to put these barriers in.
Yep. So I mean, there's nothing deep here. It's just a little kind of fiddly little issue that many people have screwed up, and it's caused bugs in Google's deployment. Lots of questions.
So just a really quick one. So you talked about how there were, in reality, there's multiple controllers and there's a protocol among them. Is that also exposed to the complexity here in terms of like keeping the controllers in sync with each other?
Of course, I'm not going to talk about that much. So one of the benefits of this is because the controllers are just ordinary machines, they can use existing software and really like off-the-shelf software to manage their replicated state. So they could run Paxos, or they could use some eventually consistent key value store, and you sort of get whatever that gives you.
Okay.
So I'm mostly going to focus on the sort of controller replica group switch consistency, not the intra-controller replica consistency. Chaz?
So you're painting the worst possible picture here, right? Now, is there a trend here that when people implement this kind of stuff in the data center, they really take, they really exploit all this freedom, and then they are changing the routing tables all the time? I mean, if things were really this chaotic, then in the past, networks should be failing all the time, right? But they don't fail. It must be the case that routing tables don't change that frequently. So all these race conditions that are happening, they don't actually manifest.
So two things I'll say. So one is that sort of a common complaint in networking is that we're sort of stuck with lowest common denominator, 1970s TCP/IP functionality. So people would like to do fancier stuff. They'd like to do more dynamic stuff, but they haven't been able to because they don't have an interface for programming the devices. So I think that's the real source of not this kind of chaotic dynamic change.
People are just in the past, people have been very conservative.
Yeah, and I mean, like if you think about renting machines from Azure or EC2, like if you're a customer and you have at least hundreds or thousands of machines, you might like to configure the network that's connecting those machines to give you some function, like maybe broadcast service, or maybe some kind of bulk transfer, with you don't care about latency, but you want good bandwidth. And so, if you imagine sort of all the customers in a shared data center wanting to program their own slice of the network, now you do get actually rapid change.
Sure.
So if you wanted that to go completely in order, you'd have to have barrier pressed in between each method?
Yeah, so in this case, I mean, I don't actually need barriers between each thing to implement my policy. The thing that's broken here is that my SSH blocking policy has been violated transiently. So all I really need to do is make sure that I start out by putting that drop all SSH traffic rule first, and then before I proceed to allow other traffic through, I make sure that that rule is installed.
But if you didn't know anything beforehand,
yes, the naive thing you could do is to put barriers everywhere. That would slow down the throughput of your controller, its ability to change the state of the network. So that would be a bad idea. But,
the question is why the priority information is not loaded in the table, like high priority.
oh, sorry. In general, I'll sort of elide priorities in some of my diagrams. You can just read them as being in order.
Okay, so there is a priority information.
Yeah, there's a field here that exactly reflects what's there.
So it seems that even if you have barriers, I mean, the fact what you really would like is atomically switch between two complete tables.
Yes.
So
Even worse, you'd like to do that across the entire network, right? Like there's
Yeah.
atomically switch from n switches in this configuration.
so
to
I'm
n.
not convinced that you can get the same guarantees always by doing little changes at a time.
So we have a paper that was at SIGCOM this year for doing exactly this. I'll talk about it at the end. Yes. So let me show you a third kind of, again, nothing deep, but kind of just a little gotcha that can and does trip up sort of network programmers. And that is, this code I showed you is a lie. In particular, the first pattern, desport 22, which I asserted, and you all believe me, matches all SSH traffic, actually doesn't. It actually matches all packets. And the reason is, if you go read the spec, which we neglected to do for a while, the way that packets are actually matched against these patterns are, you sort of traverse a bunch of, sort of starting from the Ethernet level all the way up the stack. And you only match fields high up in the stack if all their dependencies have also been matched lower. So just matching for destination port 22 doesn't make sense if you're talking about not a TCP packet or not a UDP packet. And so what switches do is they just ignore this, and they treat that like the all wildcarded pattern. So actually, this code I showed you would have just dropped all traffic. And again, just a stupid mistake, but it's a kind of low-level detail that comes from having to sort of program the hardware directly that can and has caused real bugs. So what you have to do is actually write a much more complicated pattern. It's basically there's sort of a dependent type that captures what a valid pattern is. In this case, you have to say, well, first, the Ethernet frame type is IP, and the IP protocol type is TCP, and then now you can say the TCP protocol is 22. Everything works. OK, so in sort of research controllers, some that my group has built, some that some people at Brown have built, and some that people at Yale have built, sort of all of these bugs have come up. From not having the correct packet in handler, to forgetting barriers, to generating bogus patterns, and also the problems with patterns can lead to bogus optimizations in compilers. And they can lead to essentially arbitrary behavior, where you thought your network was definitely going to block SSH traffic, and instead it's letting everything through. So in the networking community, there's been sort of a growing cottage industry in building tools for checking configurations. And this predates these software-defined networks, but they've kind of ramped up in recent years because now there's sort of a simple interface that you can actually check. So there's tools like Flow Checker, Anteater, NICE, Header Space Analysis, Veriflow, and many others. And I think actually this makes me really happy. There's sort of people not from our community who are getting excited about writing down formal specifications and checking them and having automated tools to do this. This is like awesome. So they're great tools, but they have a few less optimal features. So one, they're mostly doing basically dynamic runtime analysis. So they're basically wrapping, say, a controller with a reference monitor that inspects all the messages coming up and down, and they just check for violations of safety properties. So that makes them really slow. And second, they all build on some custom ad hoc foundation. And often these are unsound. So I won't pick on anyone in particular, but some of these tools, for example, don't model things like barriers. And so they might tell you some property holds, but actually the switches will not necessarily have that property. So one of the goals of the work I'm going to tell you about today was to actually sort of provide a principled foundation that one could use to build tools like this and actually prove a theorem that says the assertions that this tool validates are in fact correct. So our vision was to basically rethink the sort of controller stack, and in particular, use a high-level programming language to describe what we want the network to do, and then let a compiler handle a bunch of the low-level details involved in doing things like inserting barriers or generating well-formed patterns, optimizing rules and such. And to be able to do reasoning using just our high-level language and not have to reason about all these low-level artifacts. And then to make sure that all of this is correct, to build a compiler and to actually establish its correctness using a mechanized proof assistant. So that's what we've done. So we're actually building on sort of a lot of recent success in the formal methods community. So I'm sure you all know projects like SEL4 and CompCert and FStar down here that are really, I think, exciting because they're sort of taking real software systems and building them with what you might call certified techniques. So there's great tools now, ACL2, Isabel, Koch. There's textbooks you can teach to undergraduates. And so it's kind of finally becoming possible to build serious systems and to prove their correctness. So I assume most of you know how this works, but basically what we're going to do is sort of write the code that implements our controller, prove it correct against the specification, and then extract the code to OCaml, and then compile it, and we get a certified binary that we can run and have high confidence that it's going to be correct. OK, so if you're familiar with systems like CompCert, the architecture of our system is very similar. It's a sort of classic compiler pipeline consisting of a bunch of different phases and intermediate languages. And each of the arrows between these phases is going to be proof correct in Koch. So we're going to develop each of the levels of abstraction, formalized both the syntax and its semantics in Koch. We're going to build machine check proofs that the compiler, the optimizer, and the runtime each preserve semantics as you go down. And then we'll be able to extract code and run it. So one thing that is a little different from this work from, say, things like CompCert is we actually didn't have a sort of clear formal definition of our lowest level machine. And so one of the things we had to do, besides sort of build all this other stuff on top, was actually to pick out a foundational model that we could use to let all the rest of our theorems sit upon.
I have a question. Did you have to build a new backend for OCaml? Because presumably the standard backend compiles down to x86, but the control plane is not running x86, right?
No, the control plane is running x86.
It is x86.
That's the whole point, yeah.
I see.
Yeah, it's running on a Linux machine or whatever.
Okay.
Yeah.
Okay.
Yeah. So the controller itself runs on x86 right here, and then it emits OpenFlow messages that get sent down to a switch.
Okay.
OK. So let me just take you through sort of very quickly through this stack, and I'll just kind of highlight some of the interesting pieces. So first, I think some of you have seen this NetCore language before. It was at Popl 12, also this week at NSDI. It's basically a high-level declarative programming language for describing the behavior of OpenFlow networks. I think Dave Walker's coming here in a month, and he's going to talk much more about our NSDI paper. So I'm not going to kind of harp on NetCore, because he'll tell you much more about it. But you can kind of think of it just as kind of a logic programming language that specifies how packets should be forwarded in a network. So unlike the low-level things I showed you, it has sort of a rich predicate language for classifying packets by where they are and how they're structured. We have sort of declarative actions for how we want to transform packets. So we can forward them, we can modify their values, and we can query them, getting results back on the controller. And then we can combine things like predicates and policies using natural operators that aren't implemented in hardware. So things like disjunction, conjunction, negation. And this makes it very easy to write simple, declarative, easy to analyze specifications of what the network should do. So just as an example for our little toy network, here's how you'd write the total configuration you'd write in NetCore. You basically say, anything that's not SSH, forward to host 1, forward to host 2, forward to host 3, and also forward all web traffic to port 4. And that's it. And the compiler and runtime is going to take care of turning this into flow tables and then also generating all the messages to the switches.
I thought you said if it doesn't match, then it's going to get forwarded back to the controller.
So this is a different language that we've designed.
Yeah.
And here, if something doesn't match, it's just dropped.
Okay,
So we've
different.
So I've sort of hinted that the semantics of this language is sort of very natural and high level. Let me kind of make this formal. So here I have a little judgment that captures our operational semantics for NetCore. This is sort of a semantics that talks about the behavior across the entire network. So we have P, a program in NetCore. The state of sort of the machine we're running on is going to be a bag of packets located at particular places in the network. And so a located packet is just sort of a packet parked at a particular switch and port. And what this rule says is if we start out in a state with a particular packet and then sort of the rest of the packets, and if processing that single packet according to our policy generates a whole bunch of additional packets M prime, then the whole network takes a step, processing LP, and gives us the rest of the packets we started with plus M prime. So it's very simple high-level description of hop-by-hop processing. And the only kind of asynchrony is just we don't know what order packets we processed. So there's sort of just this bag of packets that are in the state.
So this is very non-deterministic, right?
Yes.
You can pick any subset and process it.
Yep. And I think that's unavoidable, right? Because you're not going to synchronize. I mean, one could imagine doing this, but it would be very expensive. So you're not going to sort of synchronize a packet over here and a packet over here and force them to be processed differently. Things are fundamentally asynchronous and concurrent. So the key things to notice are we can reason about hop-by-hop forwarding behavior. We don't have to deal with the fact that there's an underlying distributed system. So we don't have to worry about controllers and switches and messages and barriers and things. And if we want to reason about simple reachability properties, things like no SSH traffic gets through, you can do that using this model, and it's very simple.
So the way I imagine it is that, I mean, of course, right now you're just talking about the high-level operational semantics, but the way I should imagine the execution is that this program is being executed simultaneously on all controllers in the network, right?
This is the in this very abstract view, this is the entire network. So the state of the network is a bag of packets that are in flight.
Right.
And each tick, one packet gets processed and more things go into the state.
Okay. So entire network meaning all the controllers and all the...
There's no controllers and switches here, but yes.
I understand, yeah. Okay,
Yeah.
all right, yeah, good.
So our task now is to build a compiler that faithfully implements this
Yeah.
using controllers and switches.
Mm-hmm.
Okay, so the first step in our compilation is to basically take our high-level sort of logical language and turn it into flow tables. So I like to think of flow tables as sort of the RTL of network programming. So they're kind of an idealized version of what hardware supports. But we don't have to worry about things like priority yet, and also we don't have to worry about space constraints. So they're just sort of unbounded linear sequences of patterns and actions. The nice thing about flow tables is if you have a collection of flow tables, one for each switch in the network, you can endow it with the same kind of high-level semantics. All we've done is sort of change the way we represent the function on packets that we're computing. So we still don't have a kind of distributed system. We're just reasoning about sort of a bag of packets being processed one at a time.
I have a question. The set LP that you're processing in one step.
Yes.
Are those packets that are located at the same node, or can they also be in different nodes?
Sorry, I should have said this a little slower. So this is intended to be a multi-set containing just one element.
Oh, okay.
And then we're picking this one out. We're processing it by sort of interpreting the flow table. And then this generates new packets.
So that's one element at a time.
Yeah, one element at a time. So if there's actually an interesting question I don't quite know the answer to. We're doing a sort of classic, interleading model of concurrency here, and you might wonder if we need true concurrency because.
I don't really want that.
Okay. I thought that was where you're going. I went to grad school with Sebastian. He's much smarter than I am, so I get worried when he asks a question. Okay, so so our compiler is going to take these NetCore programs and generate flow tables, and it's maybe a little grandiose to even call this a compiler because it's just sort of doing the obvious flattening of our policies. The key operation, though, is kind of an intersection on flow tables. So just to show you a quick example, if we take a simple little atomic policy that just says forward from host 1, out port 1, this turns into a little one-line flow table like this. We can have another policy, forward web traffic out port 4, turns into another one-line flow table. And then we combine these, say, taking their union, and what we produce is this. So we basically have to intersect the two rules to find their common bits, take the union of their actions, and then we can concatenate the residuals below it. So this is sort of how we implement union, and the other operations are kind of similar.
The matching of this is like a up-down approach, top-down.
Yeah. So packets coming in first try to match this rule, and if not, they fall through to this rule.
And if you find a match, they will.
They take the first match.
And didn't do any matching.
Correct. So I mean, there is something to think about here because you don't have things like negation. You can't say not this. You have to encode negation by putting the thing you don't want above and then letting things fall through to what you want to have happen. Likewise for union, you have to be careful and kind of handle the overlap together and then the residuals on either side. There's not anything really deep here though. It's just, I guess the main thing is, first of all, we have to make sure that we're always generating these valid patterns to avoid the bug where patterns don't mean what you think. And there is a little bit of thought to how you implement some of the operators. When Dave comes, I think he'll tell you about a new operator we just added to NetCore, which is sequential composition, which lets us express multiple phases of processing, and compiling that is more challenging.
Now, the reverse direction is easy?
Going from flow tables to NetCore? Yeah.
you express that as a nested condition?
I mean, the naive way would be to literally just sort of, write down the atomic program for this, and then take the negation of this pattern and then union that with this. Of course, that might be a very large representation. So you might like to do something smarter, but
yes. So the question is there a size preserving transformation in the other direction?
That's a good question that I don't know the answer to offhand. So we're part of the larger Frenetic team is actually building a tool that will do exactly this. And the reason is we want to expose to other kinds of controllers some of our nice compositional policy combination abstractions. And so we can't sort of insist that everyone work in NetCore, because they don't. So actually going from, exactly the problem you said, going from flow tables into NetCore so that we can then combine them using some of these operators.
But in essence, this is a nested condition.
Yeah.
And above it's a union.
Yep. The short answer, I don't know, but that's a great question. So as you might imagine, there's sort of a blow-up that happens. So if you just naively compiled using this intersections everywhere, then you get an exponential blow-up. And so you really need some kind of optimizer that's going to at least do things like strip out empty or shadowed rules. And it turns out that these two things actually do well enough in practice to not generate huge flow tables. So overall, this sort of first phase of the compiler, when we proved it correct in Coq, what we proved was this theorem, which says for all optimizers, policies, switches, ports, packets, and buffer IDs, buffer ID is sort of a low level detail, if your optimizer is semantics preserving, so given a flow table, it produces an equivalent flow table, then evaluating in NetCore is the same as evaluating in flow tables. So
is this for a single switch at a time?
This is for all switches.
Right. I mean, is SW one switch or a set of switches?
One switch.
One switch.
So right. So another thing the compiler does, which I didn't mention, is it takes this policy that applies to all switches, and it has to generate flow tables for each individual switch. And I didn't emphasize this in my example, but NetCore includes some primitives for constraining a portion of the policy to a particular switch or set of switches.
So if you say a naive compiler produces exponentially large flow tables, is there like a separating function where you have some sort of NetCore program that must be exponentially expressed?
So I don't want to step on a limit of something I don't have, but Arjun has an argument that actually it's not exponential for as long as the number of header fields is finite, which is true in practice. But let me not. I don't want to assert that because I haven't seen the proof. OK, so to prove this theorem, we actually had to do a bunch of things in Coq. So we had to build a sort of library of algebraic manipulations on flow tables. We also had to write down a new tactic for proving equalities on bags. Sort of all of our theorems end up having to show that some bag of packets produced on one side is equal to some bag of packets on the other side. And we also had to have a sort of key invariant that's maintained all the way through, which is that all patterns are what we call natural. And I'm just going to flash this up and not explain it, which is a terrible thing to do. But this is sort of the Coq-dependent type that captures well-formed patterns. And it just says, everything you match, all of its dependencies, all the way back down to the Ethernet level, are all reflected in the pattern.
Is this slide for you? Oh, really?
Why is this next slide?
Because only he understands all this stuff.
OK, great. I only have a couple more of these, so I should.
Should be using abstract.
OK, so now I want to jump down to do this next arrow, the runtime system. But first, I have to tell you about the low-level model that we proved this against. So we wanted to prove a theorem saying that our compiler is correct. And to do that, we need some kind of mathematical representation of what the network is and how it behaves. And what OpenFlow gives us is a 42-page informal specification document consisting of English prose, diagrams and flowcharts, and a bunch of C-struct definitions. So it's hard to prove a theorem about this kind of thing. So what we did, sort of inspired by all the various featherweight systems out there, was to extract a sort of one-page operational semantics that captures, we think, the key features of OpenFlow. So this is really kind of it. There's sort of a bunch of a grammar that gives sort of a bunch of syntax, and then these operational semantics rules. And what we included was we made a choice to just model all the features that are related to packet forwarding, and also to capture all of the essential asynchrony. So anywhere where something could be reordered, we made sure that our model didn't somehow linearize things. We elided a bunch of other things. So a big part of this is related to things like error messages. And we decided not to model that, and instead we decided to sort of prove that our controller never generates these kinds of errors, so it always stays in sort of the safe subset. And we also left out things like the statistics that I mentioned earlier. So our verified compiler doesn't include support for statistics.
So this part of the exercise is only so you can prove the theorem, right? It doesn't affect the code generation or the compilation. Am I correct?
No. So I mean, we actually have mechanized this in Coq, and we have built controllers that target this model.
Okay.
We then link it with a lower level unverified library that implements the full OpenFlow protocol, and there's a small mapping between Featherweight and full that's unverified. That does sort of the obvious embedding projection.
I see.
So eventually, yes, we should sort of build a full, not Featherweight OpenFlow, so that we can do things like traffic statistics and failures and other things. We chose to do this Featherweight thing, both because we wanted to publish a paper not in 3 years, but in 6 months. And also, I do think this model is actually useful for other people. So if you're building a tool and you want to kind of reason about forwarding, don't make the mistakes that some of the other tools make, just sort of taking some ad hoc definition of what OpenFlow is. Take this thing. It's not that complicated, and you can actually prove a theorem about this thing in the way that we all do. And you'll get some confidence about a certain class of properties. So I hope, we plan to, and I hope other people will extend this model. But it's kind of our tasteful attempt to sort of extract a one-page operational semantics from the spec.
Is there some way to test the semantics against what OpenFlow is actually doing?
Yeah, so one of our collaborators at TU Labs in Berlin has actually been working on exactly this problem of basically taking formal specifications and checking whether switches conform to them. And because this is in Coq, we have an artifact we can extract. So we haven't done this yet, but we're planning to use his tool to try to find inputs where they disagree.
So I didn't quite understand the difference between Featherweight and the regular OpenFlow. Is it that there are things you can't express in Featherweight that are in OpenFlow in the full, or is it just that there's things that things that you want to express that you can't, or is it that actually it's just the details are not all there?
Both. So we left out, for example, counters on switches. So we just don't. Our switches in this model don't have counters.
Right.
And so the messages in OpenFlow that say, please give me the counters, and here are the results of asking for counters, we just don't include those either. So that's just eliding something that we didn't model.
Yeah, okay, I guess.
And so we can't then express any program that needs to do traffic monitoring.
Yeah, okay. So that was the other related question I had, which was, do people actually use counters for anything other than traffic monitoring? I mean, do they actually use them for semantically useful things?
Sure. I mean, so I don't know the innards of how Google's controller works, but they're doing a sort of continuous online traffic optimization problem. And I don't actually, so the thing I don't know is if they're using OpenFlow to gather those statistics, but they're basically taking the traffic matrix and then periodically resolving some big constraint and then choosing how to.
Okay. Yep.
So it is important. Okay, so just to kind of give you a flavor, and I think I have, 5 minutes?
No.
7 minutes?
More.
Okay, 10 minutes.
6.
So I'll just kind of show you some of the artifacts from the spec and how we realize them in our model. So here's the definition of patterns, and for us they just turn into a simple Coq data type. Here's the definition of how packets get matched that I showed you before. This turns into a nice little function. And so the point is that we've not cut corners on modeling how packet matching, packet forwarding, and flow table configuration works. All of that is faithfully modeled in our Featherweight system. We also, as I've said, didn't cut corners with asynchrony. So there's various pieces of the spec that say things like, in the absence of barriers, switches may reorder messages, or there's no packet output ordering guaranteed within a port. And so for us, this turns into definitions of various elements of our model where instead of being queues or lists, they're bags. And now the operational semantics lets you pull things out of the bags in any order.
So actually, I just have a Coq question. When you were proving theorem, does Coq natively understand bag? Or did you have to prove a library of theorems about bags that you were using?
Both. So there are existing Coq libraries, and we've tried to reuse things whenever possible. The one thing we did with respect to bags was adding some new tactics for proving equality. So we end up, in many of our theorems, we end up with sort of a bag and then map of some function over that bag being equal to some different bag and maybe function of map of, so we end up with different expressions. We wanted to basically automatically get those equalities when they were actually equalities without having to unfold definitions and apply induction hypotheses and things like that.
And also, why did we choose Coq as a vehicle for doing all this?
So first there's sort of a large and growing community of people building software in this way. I guess we could have used Isabelle. I've done some proofs in Isabelle before, but sort of just trendy hype, I guess. Coq is popular, and that's important actually because when you get stuck and have a question, you can ask your smart French friends, and they'll tell you exactly how to do something. Second, we wanted to actually run the code, and so Coq has really nice extraction features, and so.
So ACL2 also has that, right?
Yeah.
Okay.
There's no reason you couldn't do this in ACL2 or Isabelle.
Okay.
So that's our model, and now I want to tell you a little bit about how we verified the runtimes. So one thing we could have done that we decided not to do was to prove the correctness of a particular runtime system for our NetCore language. So we didn't want to do this. We actually wanted to try to come up with some more general principles for how you could prove the correctness of different kinds of controllers. And so in our model, we actually represent the controller quite abstractly. So there's sort of a type of controller state. And then there's two functions that sort of capture the behavior of the controller, an input function and an output function. And the input function takes a message from a switch and a switch and a message from the switch and the current controller state and outputs the new controller state. And then the output message takes the current controller state and produces a message to a switch and a new state. So this isn't quite the most general thing you can imagine, but as long as your controller kind of factors into these two functions, you can put it into our model. So it's a very fully is probably too strong. Nick can say fully with justification, but maybe I can't say that. But it's a quite abstract model of controllers. So now let me show you the kind of the final proof for our runtime systems. And again, as I said, there's sort of many strategies you could use to build controllers. Here are three that people have done either in toy prototypes or in real systems. So the most naive is, well, you could just not install any rules ever and use your general purpose controllers to do all processing. That's really dumb and slow, but you could do it. Another thing you could do is what we call reactive. This was actually the strategy used in sort of the first OpenFlow system, a system called Ethane that was done at Stanford, doing very fine-grained access control in networks. So here the idea is the switches start out empty, and then as they see traffic, packets get diverted to the controller. So it receives the first packet, and then it does a computation to figure out what should happen to that packet and several future packets, and then it installs a rule that handles that packet and future packets. So this is kind of a, if you want, kind of an online partial evaluation sort of happening dynamically in the network. And then the best, of course, are what we call proactive compilers. This is where you actually take some description of the function you want the network to implement and turn it into a set of rules that handle, hopefully, all traffic. So our goal was to actually come up with a sort of general framework for proving all of these things correct. And the thing I'm kind of happiest about with this work, Arjun and Mark came up with a very small number of simple safety and liveness conditions that if your controller satisfies, we can prove in Coq that there's a bisimulation between the high-level function you're trying to implement and its realization in Featherweight OpenFlow. So intuitively, what these conditions say are, first, at all times, your controller has to have the property that any rules that have been installed in the network are an approximation of the function the controller is trying to implement. So what do I mean by approximation? Just in the sense of being a less defined function. So any of the rules need to be compatible with the controller function, but they can be a little bit less defined. And then the liveness condition is just when packets are diverted to the controller eventually needs to process all of those packets in accordance with the policy. And so just to give you another little taste of Coq, this is actually all sort of parameterized in a functor. And so you basically provide your controller implementation and some proofs of these properties. And then what you get out is a weak bisimulation between the OpenFlow artifact and the abstract artifact that you specified.
Does that give you any guarantees about the behavior during installation of the rules?
So this is at all times, yeah. So this is while the rules are being installed.
So while the rules being installed, you may be dropping some packets.
So this is a good point. We don't model packet loss in our model. Any of the guarantees we give, you need to, in a real network, degrade them by basically taking prefixes of what's predicted by our model.
Okay, so
If there's no packet loss, then no packets are.
no, I guess what I meant was at any, so the controller has, okay, so at any point, you have some prefix of the current controller function being installed. Right? And then you have the default rule, which can either drop or it can send the stuff up to the controller to get processed. So there's various approaches. You could have if you diverted everything to the controller, it could basically be doing the suffix to do the rest, or
That's what I intend here.
that's what you intend.
So,
Okay.
so the last rule, I mean the default catch-all rule, which diverts to the controller.
Okay, so basically, okay, I see. So so you're not dropping the packets in the process of installing these functions. There's always going to be the default, which will send things up, and then the controller can do forwarding. So there will be some period of time during the installation where the controller is maybe a little bit of a bottleneck performance-wise.
Yep.
I see.
And let me say, we haven't really dealt with failure. So I said we completely punted on packets being dropped in our featherweight model,
Right.
and we've kind of convinced ourselves, not in Coq, that our properties degrade in the obvious way. But I think probably the next thing to do is to actually put in lossy links and buffers that are finite and things that overflow and packets that are dropped and push on that.
Can you create like temporary loops in the network? Because the routers are not updated as synchronously, right? So you could have some rule that forwards to some other router and then it comes back. And
Yes, so this is sort of the same question that Sebastian had at the beginning. Let me say this is for one policy, so one NetCore policy. So we don't create loops unless that policy has loops. If you're talking about policies that are changing over time, then you need to have some way of atomically or otherwise consistently updating a set of switches. I'll say a couple words at the very end, but let me defer till then. Okay, so let me jump to our actual implementation status and a few small experiments we did. So our total development is about 12,000 lines of Coq code in proofs and about 1,600 lines of unverified OCaml code. Most of the OCaml code is doing things like serializing and deserializing messages and also gluing up with some of the functors that we have in Coq. So the components are just sort of each of the things I showed you: NetCore, flow tables, compilers, runtime systems, and machine check proofs of correctness.
When you extract code from Coq, that's presumably OCaml code?
OCaml, yep.
How many lines of OCaml code do you extract from that 12,000 lines of Coq code?
It's probably, I could check on my laptop, it's probably about 1/3 of that 12,000. So I think it's about 4,000 or 5,000, but let me check afterwards. And so this extracts to OCaml, we link it with this unverified glue code, and we've been running it for a while now, both at Arjun's house and in the lab. So far we've deployed it on lots of software switches and also a couple of hardware switches. So in our systems lab we have this switch here, a Pronto switch that runs OpenFlow, and Arjun has this little TP-Link Wi-Fi box in his house that's running verified NetCore. And we built a bunch of kind of canonical network applications, so things like host discovery, shortest path routing, broadcast, some traffic monitoring that's unverified, but that can be linked with the verified code, and also access control. And what's kind of nice is because we have NetCore, each of these little apps can be combined together using policy union, and you kind of get both. So we actually sort of can support more than just each of these in isolation. Let me tell you a little bit about the performance of this thing. So we did 2 little experiments. These aren't sort of any kind of comprehensive evaluation, so I don't want to overstate them, but we have been running it, it's real. And the first test was, what's the throughput of our controller? So it's pretty obvious that the ability of the controller to process messages is going to be important for the performance of the network, especially if it's ever receiving packets. So there's a little benchmarking tool called Cbench that is sort of standard in this community that basically takes a bunch of switches, software switches, and just floods the controller with messages, and then just measures the time needed to generate responses to those messages. And so we ran this on a desktop machine, and we sit somewhere sort of above the Python implementation and below all the series implementations. So our previous implementation of NetCore in Haskell could do about 26K messages per second. We're at about 9.4. And the reason for this is actually OCaml has not great multi-core support. So unlike our Haskell implementation, which had a different thread for every switch, and Cbench uses lots of switches to flood the controller with messages. Our OCaml code is single-threaded, and we think that's a big reason for the slowdown. Also, some of the glue code that maps between our sort of the full OpenFlow spec and our Featherweight spec does a lot of extra copying. And so messages get sort of copied one extra time going up and down in our verified implementation. So we think this is kind of a first number. We think we can do much better.
But this was with one switch? How many switches?
So Cbench, if you run it on a multi-core machine, it actually generates sort of a bunch of software switches that hammer the controller with messages. And then the controller, if it's running on a multi-core machine, can of course do things like spawn off a thread for every switch and process them separately.
But they're coming from the same machine that's running the controller?
In this case, we ran it on one machine, one multi-core machine.
So about multi-core support in OCaml, I mean, even if you did have, were making use of multi-core in OCaml, I mean, doing the proof in COP for a multi-core, for a concurrent camel program would be much, much harder.
Yep. So I should say, I'm not sure how much we're going to stick using this verified component for all time.
But it's not concurrent, it's parallel. They don't interact.
Yeah, it's easy. Each switch has a separate handler, and for a given NetCore policy, that handler is completely static.
But you say the unverified NetCore Haskell implementation, right? That thing is a single switch. It has concurrency at the switch level as well, right? Presumably that's why you're getting this 26,000 messages per second.
No, it's actually that the controller is spawning off a different thread to handle all the messages from every switch. So when the switch connects to the controller and they handshake, the controller then spawns off a thread and then.
So actually I was a little confused. I thought that there was one controller per switch, but it's not like that. One controller can be controlling lots of switches.
Yes, yes.
I see.
So there would still, the verification task would still be much harder if you were to do a concurrent controller.
Yep.
Right?
Yeah. It would be because, right, it is controlling multiple of them, right? So there would be some communication, yes. Okay.
I mean, there's no interaction though, between what the controller has to say to one switch and what it has to say to another switch, right? I mean, there could be programmed that.
So we also did a little experiment. We actually did a bunch of them, but I'll just show you one to measure how effective the controller is at basically pushing down the policy into the network. So for this, we used a simple Waxman graph, which is a random graph that is commonly used as a model of enterprise networks with a couple of hosts per switch. And we ran an application consisting of broadcast along spanning tree and point-to-point forwarding along shortest paths. And we just used a very simple traffic generator where each of the 12 hosts periodically sent a broadcast ping, and then, of course, all the switches would respond back to that ping. Sorry, all the hosts would respond back to that ping. And we ran this with a bunch of different controllers. So top left is our OCaml verified controller. And this is a time series showing how much traffic the controller had to handle over the run of the experiment for, on a logarithmic scale. So as you can see, at the very start, there's about 60 kilobytes of traffic, which is just the controller sending down the configurations to all the switches. And then at periodic 15-second intervals, there's some keep alives that are part of OpenFlow. So this is just the switch saying, are you still there? And the controller saying, I'm still there. And these are quite small, a couple thousand kilobytes. And this is almost exactly the same as what you see for our unverified Haskell implementation. Just to kind of illustrate some of the other kinds of runtimes you can build, we also built a microflow or reactive runtime that doesn't install any rules, but then installs very fine-grained rules when it sees traffic. And so here you see quite a big difference. Sort of every time that a host sends a ping, there's sort of a huge spike in traffic because the controller's scrambling to process all of those packets that are being sent to it all of a sudden. Then it sends down a rule, and then there's nothing for a while until the next different flow happens. And then over here you see the most naive controller, which installs no rules and processes everything itself. And so here you see just a high rate of constant traffic, and when the broadcast comes and the flood of messages come back, there's a spike. So again, nothing, I wouldn't put any, this isn't like any kind of complete evaluation, but just to show you that these things are running and doing what we'd expect. Question? I don't know how much time I have, but we've also built a little verification tool for NetCore. This is what the undergrad Rebecca did. And the sort of obvious observation is once you've designed NetCore, built a verified compiler, then you might as well do reasoning about network programs in NetCore, because it's much, much simpler. So what Rebecca did was to basically take NetCore programs in a particular topology, encode them in Z3 using a model that was proposed first by Xi, and then later on some people at Stanford turned it into header space, a tool that they've been working on for a couple of years. Basically you express sort of the function that the network implements as one relation and the topology as another relation. You compose them together, take their transitive closure, and then you can check reachability properties automatically. So here's a little snippet of Z3 with all the interesting bits elided that kind of shows how we use it. We've also used Z3 to implement translation validation for NetCore. So we have a couple of extensions. Actually, Cole Schlesinger, who was an intern here before, has been working on how we can do isolation for NetCore policies. And the isolation compiler is actually just a NetCore to NetCore translation. And so to check that that translation doesn't somehow change the behavior of our policy and also gives us isolation, we've used Z3 to do that checking. So just to kind of wrap up, I think developing formal methods for networks is a really exciting area because networks are critical infrastructure and only becoming more important. But they're still being programmed using really rudimentary techniques. So there's a great opportunity for our community to have some real impact. Software-defined networks are sort of an enabling technology that makes it possible to build some of these tools. And I think exploring ideas like machine verification and high-level language like NetCore are a promising first step in this direction. Let me close with a couple of just advertisements for other stuff we've been doing, and also an advertisement for a summer school that Nikolai and I are participating in this summer. We've done a bunch of other work on NetCore and other systems based around sort of programming languages plus networks. The one that I'll explain in some detail is our SIGCOMM paper from this year. So this is the question that came up twice. Sort of how do you move from one configuration of the network to another? This involves somehow updating a bunch of switches while not breaking important invariants. So what our SIGCOMM paper proposed was a few different what we called consistency levels, where basically the controller programmer just says, please update me to this new configuration. And the runtime system does a bunch of instrumentation to craft a sequence of installations and uninstallations that have the property that any packet or set of packets going through the network will see one consistent snapshot. So we call this per packet consistency and per flow consistency. And the kind of theorem in this paper tells you that if you use that kind of network update, then any invariance of the old policy and the new policy, at least path properties, will be preserved across the other grid. So you don't have to worry about specifying what invariants you want. They're just all automatically preserved. Let me not, in the interest of time, go through all of this, but if anyone's interested, I can give a more detailed description of any of this work. So let me end with an acknowledgement. This is, of course, joint work with the three people here who did all the hard stuff, and also a big group of people at Princeton, both on the network and PL side. And the advertisement is, if you're interested in exploring sort of the application of formal methods to networks, come join us this summer. I know that, well, Ithaca has the property that I know Seattle also has, which is, most of the year is miserable, and in the summer you just don't want to leave because it's so wonderful. So Ithaca is very nice in the summer. And in June, we're having a summer school with an all-star cast of lecturers, including Nikolai. So a bunch of people who are building tools for doing verification of networks. And it's open to researchers and grad students and people in industry. So if you're interested, talk to Nikolai or me. Thanks.